floor is. Thank you.
Thank you. So yeah, exploring CPython's bytecode. First, a little bit about me. I'm not a core Python developer, so I'm not really qualified to give this. And so my approach is really not going to be like explaining from the ground up how bytecode works. I'm approaching this from the outside in, as in we all know there's these PyYC files, and you know what's actually inside them. And I'll go in and start at the PyYC files, trying to read what's inside them, and from there kind of work backwards to how the Python virtual machine actually ends up executing that bytecode. Yeah, other than that, you know, occasionally try to contribute some patches. I'm maintainer of PSI, Python System Information, which is a small extension module. I have got quite a few years of experience in Python development. I've been employed full-time at working coding with Python for the past 5 or 6 years or something. So, unraveling bytecode. So it's going to start with, as I kind of said already, starting with the PyYC files, reads what's inside them. And really the main thing is that this is not going to make you a better developer knowing any of this. It's just a waste of time. It's an interesting thought experiment, but unless you really want to go and write your own interpreter or write on Python itself, none of this information is going to be very critical at making you much better. But it's a fun exercise anyway. I enjoyed it. And the examples are going to be in Python 3. The difference between Python 2 and Python 3 in bytecode is really quite small. There's a couple of small differences, but it's very easy to see to map them onto each other. Some attributes and some objects might be slightly different named and things like that, but it's not very difficult other than that. Python is really, it's always called an interpreter, but it's really a compiler and a virtual machine at the same, in one kind of package. But whenever you execute any Python file, it will first compile the source code into the bytecode, which it will then try and store in a PyYC file if it can. Compiler actually uses an intermediate step AST, which is a whole other subject, which you store and you can modify things on the AST and things, etc., which is also quite interesting. And then once it's got this bytecode, it will execute that in the virtual machine. So the virtual machine always loads pre-compiled bytecode, and then will execute it in stack frames is kind of the context that it gives while it's executing things. This talk is going to concentrate on the virtual machine part, not really much on the compiler part and the AST transformations, etc. you can do on those. This is the only image, I'm afraid to say, that you're going to get, because I'm rubbish at making images. And I even stole this from someone else with permission. But so that's like a graphical overview of what's happened, of what happens. So the source file gets transformed to AST. You create code objects which are stored in bytecode files, and then the interpreter will load those and will execute those using stack frames. And at the end of it, you get a running program, which is what you want. I'm going to be working with this small module. It's very trivial. It skips a lot of trickier bits, things that you can do in Python, but it's sufficient to demonstrate how the bytecode works, kind of thing. So it's one function, docstring, some very simple computation, returns a number. Well, it doesn't necessarily use a number. And then on the module level, it executes that function, prints it off on the screen, a docstring at the module level as well. it's a very small, yes, it skips a lot of features of Python, but all right. I'm going to be ambitious, and I'm actually going to write an interpreter during this talk, or, well, I wrote one for the talk, that will be able to execute that little module. It's going to be in Python, so it will be slow and entirely pointless again. Yeah, it's you know, it's not like PyPy where they spend 5 years or more developing fundamental things, etc. So it's really pointless exercise, but it's really nice to demonstrate how it all works. Yeah, and it will still need Python to run, obviously. The compiler part, usually it happens implicit, so you don't notice, you just run your program, and CPython will byte compile your files if it needs to. If you do want to do that explicitly, you can use the pycompile module, which you can get to, which you can also invoke on the command line. There is another module, I think, compile all, which you can point at a directory and compile whole packages, etc. In general, you don't want to really do this, but unless you're distributing packages or something like that. I'm doing the examples on Python 3.2, and your bytecode will end up in this PyCache directory. The reason, in I think earlier version of Python 3 as well as Python 3, you just get the PyRC file next to it. There's this quite recent addition, and it makes it easier to share the same bytecode directory between multiple interpreters, which is something that's useful for distributors like Debian, etc. I think Barry Washoe put that in recently. But the good thing is you don't really have to worry where the bytecode goes, because the IMP module in the standard library will tell you. So this cache from source function, you just give it the source file name, example.py, and it will come up with the long file name. There's a couple of others, like you can do the reverse, and there's a few more functions in there. So you don't have to worry where the bytecode ends up. Before actually going into it, it might obviously be good to just explain some more, because these two optimization switches that exist, optimization between codes, because they don't really optimize anything. They modify the bytecode. Firstly, when you start using them, you will end up with PyIO files. This is a bit odd. Python is one of the only languages I know that actually uses different extension. But anyway, the dunder debug thing is actually useful. It means you can write some tests or write some extra code in if blocks, if dunder debug, or something like that. So that will evaluate your faults when you have optimization on. And you'll also skip a cert statement. It can also be useful. -02 is it's a way of making the files a bit smaller by skipping doc strings. However, you have to watch out, because actually, if you're using your doc string, you'll still lose it and you suddenly crash. But that's so that's optimization kind of thing. Well, so how do you read a PyRC file? Well, you know, in the old days, you'd say read the source and figure it out. Nowadays, you just look on the internet for your question, and someone else has figured it out already. That's a very good article about the structure of PyRC files. And essentially, it's really simple. It's a magic number, a timestamp, and a code object, which is the rest of the file kind of thing. The magic number is there for Python to know that it's got the right version of PyRC file. So bytecode files, the format changes between major versions of Python, and it just needs to ensure that, yes, I'm running the right bytecode file. And if that magic number doesn't match, it's going to recompile the source, start again. The timestamp is also used because Python always looks at the source code first. The timestamp is simply used to check, do I need to recompile the bytecode? Has the source code changed yet or not? And then the code object is actually what we'll be interested in, as it turns out. Magic number, 4 bytes. That's from my example bytecode file. That's the magic number that comes out, and you can see it ends in a carriage return and a line feed. That's not really part of the magic number. That's there to detect corruption when people FTP in ASCII mode across Windows, Unix, and Mac machines, and stuff gets mangled up. So that's just a protection against that. And then the first part is 2 bytes. It's encoded in little endian, structure unpacked, that lesser than symbol. It's little endian, short, unsigned short. And the number on my example one comes out with 3,180. It's just a random number. It doesn't matter. The only thing that matters is that it matches. If you really care, you can actually go and look at import.c in the Python source code. And there's a big docstring, a big comment where it lists all the magic numbers they've had and what they've what Python version they match onto, and sort of what they've changed in the bytecode. So actually, this one they last changed at 3.2a2, and they added a new bytecode into it. This is accessible from inside Python again via the IMP module. Get magic only gives you the current magic, but that's really everything you only care about. You just want to ensure that you got the right bytecode. Any other bytecode you wouldn't be able to understand anyway, so you don't mind about those. Timestamp is a simple Unix timestamp. Again, little endian encoded. You'll find that everything in bytecode files, in Python bytecode files, is little endian encoded. So, yeah, you can unpack those. And the example module, apparently I made a slide on Sunday. So, yeah, it just gives you the time of when it was changed. The code object, then, is actually what you care about. Again, the Python standard library is very good at eating its own dog food, and it includes this Marshall module. If you read the documentation of it, it will say, don't use this because it's not general persistence, etc. Its only real reason is there to be able to write, for Python to read and write bytecode. It's insecure, it doesn't check its input, etc. All those things, and that's why you got the magic number on the front, so that Python can be sort of sure that it's going to be all right. And the API is very simple. You just call it with the file pointer that you've got open, and it will read the rest of the file until it gets to the end of the code object. It will return you the code object and leave the file pointer after the code object. So the entire process of reading a bytecode file is something along these lines. So you open the file that you want to. Make sure in Python 3 to open it as a binary file, not as a text file. You get the magic. You check the magic number is fine. But this is bad style. Obviously, don't use assert, because when you use assert for this, you will lose the information. You'll lose it when you start using -o. So, but it's shorter in the slides. You can get the timestamp out quite easily. Struct module always returns a tuple. And then you load the code object. And in a normal bytecode file, you'll then be at the end of the file. So then you want to use the code object. But we're going to quickly jump back to the compiler now. Originally it said, use this compile module to create a bytecode. There's also a direct way in code if you don't want to have an external bytecode file. You can just call the compile module, compile built-in function. Sorry. It takes just the text, the source code. It wants to know the file name because it's used in tracebacks and things like that. The mode, which is one of those exec, eval, and single. The difference between those three modes is exec is if you want to load the whole module. It will execute the whole module in a namespace normally. Eval is for single expressions. And single is something you rarely want to use again, I think. It's a special case of eval, which is used when the interpreter, when you use the interpreter interactively. So it will, after executing the expression, it will actually print it onto the current terminal you're on. The other things, flags is something like which done the future statements you want to use. You know, you can do like done the future division done in Python 2 point something, done the future width statement and things like that. Absolute import. The flags is a flag for that. Don't inherit is again normally if you leave the defaults for those keyword arguments, you'll end up with inheriting everything in flags, what future statements are active, and what optimization level you have from the code you're executing it from. So those three parameters allow you to customize that if you want to force a certain thing. Opening the source file is actually slightly cheating. It's bad style as well because you don't really know the encoding. You should really know the encoding. I think in the token item module, there's an open function that fetches the encoding out as well. But onto code objects. The great thing about it, it's documented. In the language references, there's a data model section, and that's a very interesting section when you're looking at internals in Python. It explains a lot of those. As already mentioned, I think everything that will get executed first gets compiled into a code object. They are read-only, so you can't actually modify those at all. You can create new ones if you really want to, although it's slightly complicated. And they're a bunch of CO attributes, basically. So the code object we got back from reading that PowerIC file looks slightly like this with the attributes. So it encodes your file name in there. It encodes line number information. That lnotab is a very tight way of encoding which bytecode starts at which line number. Details of there are in lnotab nodes in the source code of Python again. It's fairly complicated, but it's a tight packing. Flags I'm mostly going to ignore. It's again things like what future statements are in use, whether a function uses star args, etc. I know we're still talking about a module, but the code object you see the same code object is used for modules, for functions, for classes, etc. It just some attributes are just not used. The name is normally, if it's a function, it will be a name function. In this case, there is no name. CO names is more interesting. This is an array or a tuple. It represents as a tuple here of the names that are used by this code object. The constants again as well. So in the constants you can see docstring, which is stored as a string. You can see the two integers. Also, none is a used constant because it's returned implicitly at the end of the module. And then you can see another code object in there. So code objects will contain other code objects, and that's how you get your functions, etc. Stack size is something that, because I'm writing my little interpreter here in Python, I don't really care about knowing what the stack size will be. CPython likes to know up front what the stack size will grow up to, because I presume it can be more efficient. And then the actual bytecode is in the CO_code attribute. It's a long byte string, really. This one, it's got the same. I omitted some attributes on the previous one, like the bottom ones here. Similarly, I'm omitting some like the file name will be on this as well, of course, etc. So everything is always there. But this one is the sum function that we had. This one doesn't have any names, which is interesting. It does have constants, though. Again, a docstring and two integers that it uses. It tells you the argument count, and it says that no keyword-only arguments, because I'm skipping keyword-only arguments for now. there are, and then cellvars and freevars is, again, I'm going to skip these, but if you've got nested functions, so you've got a function, and in the function you define another function, you can use variables from outside, from the parent function. Cellvars are basically in the parent function saying these variables are going to be used by some functions lower down. Freevars is the opposite, in the function lower down, saying these variables need to come from somewhere higher up. Other than that, yeah, I'm skipping the implementation of those. Number of locals, again, I don't really care about it. I think CPython likes to can pre-allocate stuff without knowing that. And then the actual variable names used, that is useful. That will end up in your locals dictionary. Again, the stack size and the actual bytecode, which is a little bit short in this case. So, what's in the bytecode? Again, the standard library is great at this. This assembler module, this is very good. It actually documents even all the bytecodes that are used, so you don't even have to go and read the source code. It's all right there. And there's two really useful functions. Is this show code, which will very quickly dump your code object, and you'll see a nice summary of all those attributes that it has. And this, which will tell you what the bytecodes are and what they look like. So yeah, let's have a look. If I take the function object that I have, that's how it shows it, and that's the essential things you want to care about. Yeah, we've gone over these already. And then actually looking at the bytecode, if you use this, just as a reference what the function looked like. Here you can start to see what's kind of happening. Starts the function arguments end up being in the locals dictionary of the function by the caller, kind of. So you're loading the variable onto the stack. So Python is kind of a stack-based virtual machine. So it's got this stack, and then it's got this couple of arrays, the variable names and the constants, where it can look up to all the arguments. So maybe I should first tell what the different things are. The numbers on the first line is actually not line numbers in the source code. This one is then the address of the bytecode, which is just an index into that string, of that byte array in the CO code object or attribute. Then you've got the name of the bytecode. And then the last column is the attribute, which is always a number as well. But depending on the bytecode, that attribute, that number means look up something from this constants array, or look something up from this names array. And between brackets, the disassembler does this already for you, so you can nicely see what's happening. So this one is loading the variable A. It's loading 2. It's multiplying those, and then it's storing that again. So it's loading A onto the stack, it's loading 1 onto the stack, then it's multiplying those. Multiplying will pop those 2 off the stack, and then will push the result back onto the stack. And the result of that, it will store again into a variable. Same for B and for the next block. The next line does the same kind of thing. And then, yeah, and then at the end, it just works through it like that. At the end, returns a value by pushing it on the stack, I think. We'll go back. So, as I said, these are the bytecode names. They are documented in this module and tells you what they do, which I sort of set already. It also says what happens from the stack to the stack, etc., which is all very it's very helpful when you're trying to understand what the bytecodes do. So this is where you should really have a nice sort of picture of how the VM kind of works with the stack and the various arrays, but I'm not great at pictures, so I wrote a class instead. And this is my own class implementation of frame kind of thing. Python has a frame object, but and which is kind of looks the same, like, well, similar-ish. Fback, fcode, etc. I took the same names as Python does in there, just to make it simple. Back is just the previous frame, so the frame of the caller. Code will actually contain the code object that this frame is going to execute. Last I is the instruction pointer to the bytecode, so you know where in the bytecode byte array you're working. And then 3 dictionaries for the globals, the locals, and the built-ins to look up. And the last one I'm doing is the stack, which I'm doing slightly unconventional, I think, by putting this into the frame. So I'm creating a stack per frame kind of thing. Usually you have just one big stack, and when frames come and go, they've just got a stack pointer saying, I'm here in the stack kind of thing. It was quicker and easier to do it on here. And the execute method here is what we're going to build up now. And that will be able to run through the bytecodes and actually execute it. So it's a long byte. The actual bytecode itself is a long byte array. If you want to read it like more in a better way, it's kind of transfer it into integers. And these are the bytes. They're integer values. So you can sort of see from here that the first bytecode was load fast, I think, which is 124, and then 00 is its argument. So arguments consist of two numbers again that are combined. Again, little endian encoded, unsigned. So the next bytecode will be 100, which I can't remember what it was. But again, the this module is really, really useful. It has a list of all the bytecodes, so you just get the index and you know its name. And again, it's got a mapping the names back to the numbers. So it's really nice to have to look into. This module, there's another thing. This doesn't have arguments. It's 90 currently, in this version anyway. Don't rely on it. And that's what you can use to know whether your bytecode takes an argument or not. So all bytecodes that are larger or equals to 90 will have an argument. All bytecodes that are lower than 90 won't have an argument. Arguments, 2 bytes, little endian encoded. So, like the first go at writing an eval loop to evaluate that bytecode. So get the actual code in the byte array, and just making it a shorter variable. Initializing the instruction pointer, and then the actual loop in CPython itself it's an infinite loop until someone breaks out of it. So it's really easy to break Python or make it segfault, etc. by fudging the bytecode. If you hand or if you just chuck random things into the bytecode, or if you hand model the bytecode, you can actually. It's not that hard to make CPython crash, and so that's why bytecode is really a trusted thing. It needs to work, needs to be correct. I decided the actual bytecodes are again slightly up maybe, but it's quicker to just create them as methods onto the same frame object. And you basically loop through, so that's what I do with the get atta. So you loop through all the bytecodes. After you've executed a method, you want to increase the instruction pointer. That depends on whether it's got an argument or not. There's one opcode that I'm treating specially here. It's to break out of the loop, is the return value one, which just pops the stack and then returns that value. Passing arguments is kind of passing arguments is kind of tricky as well. The arguments are they need to, when you call another function, they need to be passed into, they need to be put into the locals dictionary of your new frame that you just created. The code object tells you what your argument count is. but I'm checking that in this case I just decided to want the arguments passed into the in my exec method here. So I'm checking that they're fine. I'm also, again, with assert, which you shouldn't do. I'm also checking that, because I'm not dealing with keyword arguments for now, I'm also checking that those are not used. And then the position of the arguments is actually important that they get passed into, because that position, the first argument will be, you will have to look up in the code object again, the variable names, and the position, the index of position will be reused there. So that's what the enumerate loop does. It gets the index position of your argument, and that's where it looks up the name, and then it knows that the value it got, or the object it got, needs to go in that name in the locals dictionary. So that's the receiving part of passing arguments. Other than that, that's the only thing extra to the exec loop for now. So handling bytecodes. I'm doing them as methods on the frame object here. Just a quick review of this output again. So that's what you're going to be executing. There's the simple ones: load fast, store fast. They just need to look up their arguments are all integers, so they need to look up in the right array, which in this case COVAR names, and put them from the stack into the locus dictionary, or the other way around. Load const needs to look up in the constants array. That's all pretty straightforward. Binary multiply. It's basically most binary operators work very similar. If you remember the object protocol in Python, basically multiply is actually implemented, or can be implemented in Python again itself. So you need to look up the done-the-mul operator, which is generally called on the left-hand object with the right-hand one. So that can have a go and return a value. If it doesn't return a value, if it doesn't know the other object or doesn't know how to multiply with the object, it just says not implemented. And then Python will try the other object and say, do you have a mul method? If so, do you know how to multiply yourself with the first object? That's what this loop does. It needs to pop those values of the stack, needs to and then it just checks whether that done-the-mul method is available, calls it, and then at the end, if none of them know how to multiply, you get a type error. Otherwise, result always goes back to the stack. So bytecodes just operate on the stack. Result. Sorry? I'm not, okay, possibly, I'm not sure. I would have to check that, but it might be, yes. Binary add. Very similar. Basically, well, almost the same, just another method. But again, possibly radd as well, I imagine, if it's rmul. Other than that, it's exactly the same. It just calls the two object, tries to cheat. Do you know how to add yourself to the other one? Return value is actually nothing in this case, because we already special cased that in the eval loop. So the return value is not going to be, it doesn't do anything. The return value needs to pop the stack and then return that value to the caller, basically. So the tiny VM that I've been building so far, it can actually execute this method now. If with this code, if you create a frame with the code object for some, you execute it with some parameters, it comes out with the right result, executes that entirely. So, time to look at the module. The module is a lot bigger. It doesn't fit on the screen. Again, you can see sort of do things we've seen already. Loads of docstring and modules to actually get this assigned onto doc explicitly, and functions kind of happens implicitly when you create a function object. But on line 4, it gets more interesting. It loads this, again, loads a constant, which is a code object in this case. Then it calls this make function thing. And make function is actually where it's going to take that code object and create a function object out of it. It will then take that function object and store it into another variable. It's using store name now instead of store fast. There's a subtle difference there. Similarly, the next line is line 11. That was the if statement, if name equals main. So the if statement load name, load const, both of those will end up putting something on the stack. So now you've got 2 new items on the stack. Compare up will take those 2 items on the stack, do the comparison, and put the result back onto the stack. The next is the actual if kind of statement. It takes the top of the stack again, and if it tests whether it's false or not. If it falls, it will do an absolute jump. The argument here, 49, is actually the address in the bytecode array again. So it is the address of the bytecode, the next bytecode that you want to execute. And I think I split it over 2 slides, yes. So the last is duplicating slightly a bit. And then if it's not jumping past this, so these double arrows bits, the double arrow bits is the jump label where it goes to, which is something else that this gives you, which is quite nice. Now, but what we see it doing now is it's basically loads 2 names again, which is print and sum, which is 2 functions. So they'll be popped onto the stack, 2 function objects. Then it will put 2 constants in, the 2 integers there, 15 and 4. It will again pop those on the stack on top of the function object, and then it will call the function. So that's how parameters are passed to the function. They are pushed onto the stack, and then the call function will pop those off to the stack and give them to the new frame in the correct way. You can see nested calls as well. So call function will then push back on the stack the result of the function call, and the next function will have that as its argument and pop that off the stack again to execute. Call function will end up removing because the function is still on the stack as well, so it will end up removing the function off the stack too. There's a jump forward there. That's a relative jump. I'm not entirely sure why the compiler put that in there, because it's just moving to the next bytecode. It's actually not doing anything. Jump forward 0. And at the end, load constant. It loads none and it returns it, so that's what the module kind of returns. So the new bytecodes, store name, that's pretty straightforward. You just get stored into the locals dictionary again. You need to look up the name in the right array again. See our names in this case. Load name is and this is where you can see why we had load fast earlier. Load name needs to actually check where the name comes from. So it starts with the locals dictionary. If it's not in the locals, it will try the globals. If it's not in the globals, it will look at the built-ins. And that's why load fast was kind of because the compiler sometimes knows it will be in the locals, and in that case, it will put load fast in there, so it doesn't have to do all those lookups, and it's a lot quicker. When doesn't it know? There's a load fast, there's a load global, I think, as well. So sometimes the compiler knows, and then there's load name. If you use a global, the global statement in a function, so if you use that, it knows it needs to go to global. But if not, if you haven't used the variable yet, so it needs to go back and look outside. name error if it doesn't find it, and puts the results back onto the stack. Make function then, not quite the right size, but yeah, this one doesn't handle default values, doesn't handle keyboard arguments either, keyboard only arguments. But basically, it pops the function. Pops the function object of the stack, and then it will from that it will create a function object. It pops the code object of the stack, and create a function object from it. I could have defined my own function object, but the types module in Python lets you create new function objects from scratch by function type. All it needs is the code object, which I just popped off the stack, and the globals dictionary. Puts that back onto the stack, and now you've got a function object around, which will probably be stored in a variable next. Function objects have a couple of attributes that you might have encountered. The code object you've referenced in there, you've got quick access to the module, etc., so you don't have to go via the code object to find those things. Its counterpart, call function, is more interesting. So, again, not handling default values and keyboard-only arguments. Its argument of that bytecode gets is actually split into. It treats it as two separate numbers, each byte, and one of them is the number of arguments, which includes the ones with default values. The other is the keywords arguments passed in. I think that's keywords only arguments. So yeah, you have to split. It decomposes that again by some shifting and anding together. Again, I'm skipping keyword arguments, and then the next thing it needs to do is, for each argument, it needs to look through. It needs to pop the arguments from the stack. In this case, they're just the positional arguments, and they'll be on the stack in the right position. Keyword arguments would be as the key name, and then the value name would all be on the stack. They need to be popped in the right order. So I'm popping them all off the stack. I need to reverse them to pass them onto my function. And then the next thing is you need to differentiate user functions and built-in functions. So I'm checking, basically built-in functions won't have a done the code attribute. So I'm checking whether it's a user function using that attribute. If it is, I know I can create a frame again, which I'm using to execute it. I pass in the right, I pass in the globals and the code, and the code object it needs to create a frame for, and then execute it with the arguments. If it's a built-in function, I just call it directly, print as a built-in function, so I had to put that special case in. And, well, the built-in code will do what it does. Will do the right thing. The return value of calling that function needs to be pushed back onto the stack again. I think I've said this already. So, yeah, the thing that you can... The number of arguments, the thing that you can learn from that actually is the number of arguments is you can have maximum 255 arguments passed onto a function because of that bytecode, how that bytecode argument is used. That's a hidden limitation somewhere in Python. Yep. Pop jump is false. It's pretty straightforward. You need to change the target, the instruction pointer with the target. I'm doing -3 because I know that the eval loop will actually add 3 straight after this function returns. Which, the eval loop just adds 3. Jump forward, it's very straightforward, just update the instruction pointer. Pop stack is just discarding the argument really. So if you don't care about return value of a function, like we don't care about return value of print, that's why we got pop top in there. So executing the entire module then, we see in the first part you get the code object. Next, you can create the code object, and that whole frame function that I made is actually able of compiling, creating that whole, executing that whole code object, and it prints out the result, which is all very good. This is very incomplete. Obviously, I've mentioned most of the limitations, but it gives you an idea of how the bytecode interpreter kind of works, how it uses those bytecodes, what you can sort of do. And one of the things I skipped was extended args, because bytecode, if you don't have, it's a bytecode that adds extra information onto, if the argument, because you're limited to 2 to the power of 16 argument. Sorry? Yeah, it's unlikely, because the sort of things you're looking, this is arguments that they go into the array of var names, array of names, constants, etc. It's unlikely to have more than that many. Yeah, I'm supposed to stop now. There's like a very quick thing of what people have done wrong with bytecode. Really, you don't want to do those. There's a couple of modules that help you making handcraft bytecode if you want. People have managed to do goto. People have some people. Actually, this is actually slightly useful. This is for the coverage package. By changing the line numbers, he managed to get more coverage out of it. Decompiling obfuscation. Obfuscation is quite bad because you can't read tracebacks anymore, so it's not a great idea. Yeah, and I think Armin Ronacher did mention some quite horrible things in his talk earlier this week. A switch statement has been implemented as well. And yeah, that was it, I think.
So there is room for some questions. Let's have a direction. So you can pass the microphone beyond you.
Question. Okay. Good. Maybe a stupid question, but why do you need always to use the underscore methods? For example, when you multiply, you do underscore underscore mul, and then instead of just using the multiply operator, what's the difference?
That's the way Python multiplying is implemented as a protocol. So if you create your own class, you can define that method underscore underscore mul, and that's the protocol that Python uses to multiply. So it means you can overwrite multiplication and things like that. And the way of looking up that mul method, passing in the other argument instead of just using multiply. I mean, I could have done that directly indeed because I'm skipping many things already anyway, but that's how the Python protocol kind of works.
Because, I mean, when you check the mul and do all the things in the binary multiply function, you could just do a multiplication and then the exception is raised automatically by Python if the mul is not found. So there was just one line instead of all the things.
Yeah, I just wanted to show what, if I would have put in a multiplication of the two objects, it would have had the same result. I just wanted to show that how it would actually have to do it.
Okay, thanks.
Okay, so first of all, you do need the rmul and radd and all those. That's used if you for the right-hand side. So consider division, where 3 divided by 5 is very different from 5 divided by 3, or multiplication with a string and an integer. The other thing was there was a question about global, and so I wanted to say very quickly exactly how global works. When CPython generates the bytecode for something, all locals are stored in the locals dictionary, and then there's a post-processing step after the compilation of a function that scans over and looks for assignments. Whenever it finds an assignment, it says, aha, this can be a load fast, and it converts all the references to that variable into load fast, store fast. So that's why whenever you assign something inside of a function, it occludes the global that matches that. So you have to, in order to in order to be able to assign to a global, you have to say global, and then in Python 3.2, non-local as well.
So, any more question? Nobody? Okay. Thank you, Dan.